Good afternoon. So, last part of the program, just the three applications of the chapter directed graphs. Then I'll show you also something else out of the program, or the exam program. Okay, this first application is in this sense just to show you that you can have something which is not at all geographical as we generally think. We have used quite a lot of points on the plane or in the space, but we have already seen that these points can actually represent something which has nothing to do with geometry, okay? As it was the case with the professors and the classes, and also the various situations of wolf, cabbage, and goat, and such things. And this is a job sequencing problem. You have a single machine, and that machine can actually perform different jobs, okay? Jobs which you can order from 1 to n, and but you have times of retuning or reconfiguring the machine from one job to the other, okay? And so you can have n points representing each a different job for the machine, and the complete graph, complete digraph, meaning that you have an arc from each vertex to each other vertex, okay? And on each arc you put the time of reconfiguring the machine from the job which is the tail to the job which is the head of the arc, okay? And then if you have to use to perform all the jobs, what's the best sequence for doing it? It is a directed Hamilton path. Directed meaning that you have to follow the arrows while you touch all of the vertices, and in particular it has to be a solution of the directed problem of the what's the name? Commesso viaggiatore. It's written there. I'm sorry, I'm not yet a traveling salesman. Okay, it's the problem of the traveling salesman with the fact that he only has one-way roads. Okay, and so you have to consider also directions and, of course, lengths, distances. In this case, distances are not distances; they are reconfiguring times of the machine. And so if you make a directed Hamilton cycle or path, minimizing the sum of the weights that you have on the arcs, you are actually planning the best possible route among all possible jobs the machine has to perform. Okay, just to say how many things can be formalized and solved in terms of graph theory in this particular case of directed graph theory. Okay, a singular thing is this: designing an efficient computer drum. Now, it's not actually something you want to do, but to show it again, in order to show you how different techniques in graph theory can help to problems which apparently have nothing to do with points and lines. Okay, and this is the idea. You have a rotating drum, and you want to recognize it by means of a set of electrical contacts. Now I have like this. Okay, you have consecutive contacts on the boundary, on the margin of the disk. Okay, and you have to understand what the position of the disk is just by these four contacts. Okay, in the sense that on the disk itself you put insulating or conducting areas so that when the contacts touch the margin of the disk, they either receive a 0 or receive 1. Okay, and out of this, in this case, 4 tuple of zeros and ones, it should be possible to recognize the exact position of the wheel of the disk. Is that possible? Yes, it is. And let's see how we can do. Consider how many different positions you have to distinguish. Okay, and let's suppose that they are a power of 2 to simplify things. Okay, if you need less than a power of 2, some will be left without meaning. Okay, anyway, the application I'm going to show is valid for recognizing 2 to a certain power n different positions. Okay, and what you do is to consider k greater than or equal to n. Okay, and you define a digraph in this way. The vertices are, be careful, n-1 digit binary numbers, or if you prefer, which is actually closer to the reality, not consider them as binary numbers, but consider them only a string of n-1 binary digits, either 0 or 1. Okay? These are the vertices, so n-1 tuples. Okay? And you put an arc with which vertices do you connect by an arc and in which direction? It may sound strange. Take one vertex which is in this way, in this form. Forget about the first digit, okay? Then you have a long queue of P2 up to Pn-1. Then search for that particular queue as initial part of another vertex. Okay, so that you find another vertex Q1, Q2, Qn-1, in which Q1 equals P2, Q2 equals P3, and Qn-2 equals Pn-1. Okay, then you put an arc with tail the previous and head the second vertex. Okay, not only, but you label that arc with the initial digit, the common block, and the final digit of the second vertex. Okay, now you get a directed graph. And also you have that at each vertex you have an in degree equal to the out degree, so that it's possible to find a directed Euler tour. Okay, well, if we follow a directed Euler tour, then we'll get the wanted sequence of digits on the margin of the drum. Here it is represented in the case in which we have 16 elements, okay, and instead I'm going to do that with the half of them, so 8 places on the margin of the disk, okay, so that we follow what happens.
Okay, we have to distinguish these, all right? And so we now do what? Our vertices will be pairs of binary digits. So I'll have 1, which is 0, 0, 1, which is 0, 1, 1, which is 1, 0, 1, which is 1, 1. Okay? Now let's see our arcs. So 0, 0. Forget about this. This is a little bit misleading. It's better what you have on the book, but I'm just going to show you how what is on the book is built, so that you can better read what is on the book. Okay? Because the book has a central part which is of 2 digits, while we have a central part which is of 1. So here is a tuple, a pair of digits. Forget about the first digit and look for this as a starting part of another. I have that this is this, okay? So I have an arc going from here to here, and I label this arc with the whole of it. 0, 0, and 1. 0, 0, and 1. Okay? Now, 0, 1, 1, 0. So I have that the final block of this is the initial block of this. So I have an arc going like this, and it will be, so this time we have this, which is this, and so I have 0, 1, 0. Okay? Here I have 1, 0, and so I have that this final part is the initial part of this. So I'll have an arc like this. So, which is, and here the label will be 1, 0, 1. Okay? Here I have 1, 1, and so its final part is the initial one of this. So I have an arc going like this, and it is 1, 1, 0, the label I have here. Okay? Also, 1, 0, the final part here is 0, which is the initial part here. Okay? And so I have from here to here, and I have 1, 0, 0. The same way I have 0, 1, 1, 1, and so I have this arc, and the label here is 0, 1, 1. Okay? And I expect to have in degree 2 and out degree 2 at each vertex, and here what happens here and here. Okay, don't look at the book. So 0, final part 0. Can you find something starting with 0? Yeah, yes. Itself. Okay, 0, 0, 0, 0. Okay, and so this will be 0, 0, 0. And again here 1, 1, 1, 1. And so 1, 1, 1. Okay? Now we can build a directed Euler tour. So let's start from 0, 0. Okay? But I'll write down the edges I'm following. So I'll trace my Euler tour like this. So 0, 0, 0. Now I go down. 0, 0, 1. From here, I can go, I have two possible choices. What do you want? To stay down or to go up? Go. Zero, 1, 1. Okay. Now, of course, it's better I need to do the loop, otherwise I cannot go on with all this. Okay. So one, 1, 1. Now have to come down. 1, 1, 0. Now go and come. 1, 0, 1. And after that 0, 1, 0. And finally 1, 0, 0. Look, this is like this. This is like this. This is like this. This is like this. And again, and again, and again. And finally, okay, which means that actually we have what we wanted to have, meaning that we have that the final part of the tail is the initial part of the head, and so on and so forth. Okay, but also look at this 0, 0, 0. You can forget about this because you find it here. So it's 0, 0, 1. But if you can forget about this because it's here. So 0, 0, 0, 1. But you can forget all this because it's here. And so actually what you have is that you can read all your what you're doing out of this line here. And so this is what we can do. I just follow 0, 0, 0, 1, 1, 1, 0, and 1. And now, if I pick up 3 contacts, like in the book, okay, all the readings will determine exactly one position of the disk, okay? Just to show you, think, Euler, what was the beginning of the story? A puzzle in a pub, okay? The pub saw Königsberg, and they, over bottles of beer, they were discussing, can they do that type of tourist in the town. And we finish with something which permits to design the contacts on
computer drum. You don't design computer drums, still you can see what's the power of mathematical formalism, which takes something in an area, maybe even from a puzzle, from a game or something like that, and then formalizes it, finds regularities, finds theorem, and then we can have a fallout of concrete importance. Okay, that's one. That's the second thing I wanted to show you, and the third is instead a bit more than an application. The problem is here it is an undirected graph. Can you make it? But it's a very concrete problem in our old Italian towns, small villages. I hope that you can find the time and the money to go around some small villages of Tuscany, Umbria, but also our Romagna. Okay, there are very many small villages of very long history. They are from the 11th, 12th century, and they are very nice and something which would make millions of dollars if such villages were in the United States, I guess. Okay. And you can find, and you can go through them just with train ticket. Okay, so please find a moment to visit our towns. But they are with narrow streets, of course. Okay, and so think of having such a town, and you have to design all one ways because everything has to be one way. And you want, of course, that it is strongly connected, di-connected, okay? So that from each crossing you can go to each other crossing of the town by following one ways. That's not a trivial problem, you see? We have seen that a connected graph, if you didn't take care, you didn't care of the orientation, it is at the beginning of this chapter. It is perfectly connected, but if you look at the components, you find that it has several components, and so actually that you cannot go from each vertex of that graph to each other vertex because that's forbidden by the one ways. Okay, and so how to design one ways in order to get di-connectedness, and this is possible if the starting graph is too connected in the sense that of the chapter connectivity. Okay, the theorem is this. If G is two-edge connected, then G has a di-connected orientation. With this two-edge connected, it means you need to delete at least the two edges if you want to disconnect the graph. Okay. Given it is connected, and you need to delete at least two edges if you want to disconnect the graph. It is possible in that situation by this exercise, which we didn't do and we are not bound to do, we just trust that exercise, then we actually know that G contains at least one cycle. And then we can start with the cycle G1 and recursively build more and more subgraphs, one out of the other in a simple way, which is this. I'll do it on the two connected, actually 3-edge connected graph, which is given in the book. That is even 3-edge connected. Okay.
This is even 3 edge connected, okay? But it's all right. The idea is this: since it is at least 2 edge connected, it contains at least 1 cycle. Let's pick up a cycle here. I can have this cycle, for instance, okay? And I call it G1, subgraph G1. Being a cycle, I can give an orientation, making it in directed cycle, okay? Any of the 2 possible orientations. This one, for instance, okay? Okay, are we finished? No, there are some vertices left. Okay, pick up any of these vertices, okay? For instance, this maybe, okay? And the exercise we didn't do tells us that it's possible to find 2 disjoint paths from that vertex to the subgraph we have already settled, okay? I pick up this, and so I can find this path and this path. All right? Now what do? I orient these 2 different and disjoint paths, disjoint up to this vertex, one in one direction and the other in the other direction. One coming from G1 and the other going to G1. Okay? And all this will be G2. Okay? Now, are we finished? No. There are other vertices left. Okay? For instance, I have this vertex. Okay? And so I pick up this vertex. And again, I have one path, two disjoint paths, and I orient one coming from the already settled graph, and the other one going towards the settled graph. Okay? Am I finished? No. I have still okay, but now let me call this G3. Okay, and now we end up by picking up this, for instance, and finding one going and one coming path. Okay, now I've reached all of the vertices, and I'm sure that at least through these arcs every vertex is reachable from any other vertex. And what about the arcs we have not touched? Orient them as you like. Okay? Is that clear? So, out of a 2-edge connected graph, you always can find an orientation making it diconnected. Okay? All right, I've not ever tried to do that with the initial graph that we have. I don't remember how it is, if it is 2-edge connected or not. Okay, also this is 2-edge connected. So why not? We can try to do that, the same thing, the same trick on that one. Okay?
but now I erase all the orientations because I do them from scratch. It's like this, isn't it? Okay, so let's start from this. Okay, and I orient it, and then I pick up a vertex like this, and I find a path going, two different paths, for instance this, and I orient it going towards what I already have, and I have another here, and I orient it the other way around towards that vertex. Are we done? No, because we have this vertex, and so I have again to find one coming, one going, and I can use this, and I make it going, and this, and I make it coming. Okay, and now we are done, and every vertex is reachable from any other vertex by a directed path. What about the remaining edges? Orient them as you like. Okay? Any questions? Okay. This ends the program. Next, I want to show you rather rapidly the content of an important chapter out of the program, but I think that it's important to show you what it says, and it is networks. Okay, you have a network in which you have sources, meaning a factory is producing goods, okay, and final users, okay, absorbing markets, if you want customers, absorbing these goods, all right? And you have intermediate roads and distribution nodes, okay? And so we have a graph, and the directed one, okay, in which you want to make these goods flow, all right? But you have on each arc, you have a capacity, meaning the maximum rate of transportation of the goods themselves. And now you can understand that, for instance, this is extremely important for communication networks. Is still surviving some telecom student here? Okay. All right, so you can understand that even if it was designed 1977 is the book, and even much older, all the theory of networks, when you had no problem of web or something like that, you can understand that this is important for you, okay? And so you have these functions, a non-negative capacity for each arc, okay, and you have a function. You are looking for functions. Oh. Allora non capisco. You're looking for functions which represent what you are actually sending through the different arcs, okay? And these functions must are the quantities that you can that you make flow through that particular arc, and necessarily, well, it is a non-negative, means you are sending at something, and it is limited by the capacity of the arc. Okay, and consider that for each vertex you have what you call f minus of that vertex, which is the sum of the values of f on the incoming arcs, and f plus the sum of f on the outgoing arcs at v. Okay, and what you have is that you have what are called the intermediate vertices. You have sources, sinks, okay, sources which can have F plus. You take the set of the sources. That's the set in which, if you sum up all the F plus, you can have something greater than F minus. Okay. On the contrary, the set of sinks has the opposite situation. That the F minus overcomes F plus. In the intermediate vertices, you must have that F minus equals F plus. So they don't produce, they don't absorb, they just transmit goods. Okay? And you want to know how much can I, what's the biggest, the largest F that I can make flow through the net. Okay? We simplify the thing by adding a fake unique source, a fake unique sink. Here, these are the sources, x1 and x2, and these three are the sinks, okay? Note that you can have also that the sink sends something to another sink, all right? But this makes things more complicated, so we add one single source and one single sink. Okay. Oh, this is an example of a flow where you have that the value f is bold here, and the capacity is the normal character. Okay, so you have here capacity 6, and the flow through it is 1, so it's okay. And actually, you have that the rule that f is less than or equal to a capacity is always respected. Okay, and sometimes you also have that you have nothing flowing through these arcs in particular. Okay, so you add this fake source and this fake sink, and you do it by adding arcs with infinite capacity. All right. So now the problem is only one source, only one sink, and all the others have that the incoming flow equals the outgoing flow for every other vertex, including the true sinks and sources. All right? Now, okay, this is how you adapt things to these new, this new source and this new sink. Okay, and now we have to consider cuts. Yes, because cuts are very important, and you can understand that if you, as usual in mathematics, go to an extreme situation. Imagine to have a cartilage. Okay, everything here, everything here, a single bridge, because these are two islands, and you have a single bridge between the two. On island A, you have the unique source. On island B, unique sink, and you have a bridge. Only one bridge. Evidently, everything is conditioned, it's constrained by that bridge. What's the capacity of that bridge? You can do whatever you want on the whole network, but you must consider what the bridge it can accept. Okay, what's the generalization of this? A cut. Okay, and so an edge cut. In this case, a cut, we have to consider directions of the arcs, okay? And so you pick up a set of vertices S, its complement S bar, and you consider the arcs going from vertices of S to vertices of S bar, like in this case, okay? And this is a cut. So it's not, if you forget the directions, it is not an edge cut, okay? So the name cut is for distinguishing the two situations. Just going from S to S bar, okay? And this is what constrains everything. In the sense that if you have, okay, now a convention, an arc is said to be F0 if the function of that, the transportation on that arc, what we are making now a flow through that arc is 0, F positive if it is a positive value, F unsaturated if that what we make go through that arc is strictly less than the capacity, and F saturated if what we are making making flow through that arc equals the capacity of that arc. Okay. Now, the capacity of a cut should be, it's here. The capacity of a cut is the sum of the capacities of all these arcs. Okay, and now what you have is that the value. Sorry, I need also this. The value of F is what gets out of the source, of the sources in general, of the source in our simplified case, okay? Which is equal, it can be proved, it is equal to what answer the unique sink, okay? But the value of F is that. And what about the value of F with respect to capacity of a cut? You have that necessarily the value of F is less than or equal to the capacity of each single cut, all right? And so, necessarily, a corollary, if you have a flow, and you have a cut, and the value of F is equal to the capacity of K, then F is necessarily a maximum flow, and K is necessarily a minimum cut. Okay? It's the generalization of what we were saying about the presence of a single bridge of a cut edge, of a cut arc, so to say. Okay? Not only, now you know what's the value, the highest value of a possible flow. So you just have to consider all the capacities, to go and look for all possible cuts, and then you take the minimum of these, of the capacities of all cuts that you meet, and that will be the maximum value of a flow that you can build. Okay? But the theory goes much beyond, because it tells you how to build such a maximum flow, and the idea is really very nice. So I'll show you now this, and then we'll have a break. Okay, so. Consider that you have a flow in a network, okay? Now take a fixed path, not a directed path, a fixed path, okay, in which you can, forgetting about directions, just a path in the underlying undirected graph, okay? Now, you consider this iota, this is Greek letter iota of the path will be the minimum of the iota of the arcs on that path with the rules I'm going to show you, which is if A is a forward arc, meaning you are going from here to there, and the arc A is in the wanted direction, then you take as iota of A, C of A minus F of A. So the difference between the capacity and the value of the flow, okay? If that arc which you meet is in the good direction, with what is called a forward arc. But in this path you might also have a reverse arc, so an arc which actually goes towards you in the opposite direction of your path, okay? In that case, iota is simply the value of F. Okay, and what do we want actually? Just let's think a moment. Okay, we want not to have a flow going towards the us. Okay, so that F is something bad that you want to annihilate, to make it vanish. Okay, and on the contrary, if you are going, if the arc is in the good direction, you want to fill that capacity, and so you want to, if possible, to make F grow inside that gap C A minus F A. Okay, this is the basic idea, and okay. A path is said to be F saturated if iota of P equals 0, F unsaturated if iota of P is greater than 0. And what does it mean? If it is F unsaturated, what does it mean that you have this iota of P greater than 0? Remember that iota is the minimum that you have on the arcs of your path, okay? If you have that it is that this minimum is greater than 0, two possibilities, okay? Either no, surely what happens to all forward arcs? They are unsaturated. Otherwise, you would have 0. If even just one of the forward arcs were saturated, then you would have 0 there, and 0 would be the minimum because all these values are non-negative, okay? And each reverse arc has to be positive, meaning you have something which is flowing against your the direction of your path, okay? Again, if you had just even a single reverse arc with F equal to 0, that 0 would give us the minimum. So F of P greater than 0 means all these things. All reverse arcs positive, and all forward arcs unsaturated. Okay? An F incrementing path is an F unsaturated path from the source X to the sink Y. Okay? So we are looking for such paths. Okay, that's the idea. If we find an F unsaturated path which goes from source to sink, then it means that there we have the possibility of increasing our flow towards from source to sink. Okay, and how do we do it? With something which looks a bit like Dijkstra's algorithm. Okay. Again, we have a preferred vertex, in this case, the only source X, and we make a tree grow, okay? And we make this tree grow, and if we touch Y, we are done. Let's see how we do. So, theorem: a flow is a maximum flow if and only if it contains
if the net contains no f incrementing path, such path as we said, okay? And in any network, the value of a maximum flow is equal to the capacity of a minimum cut. And now how do we do? The labeling procedure is like this. A tree in T in M is an F unsaturated tree if the source belongs to its vertex set, and for every vertex V, the unique XV path in T is an F unsaturated path. Okay? So we want to reach all vertices in this way. Such a tree is shown here. Okay, let's see how we do now. We grow an F unsaturated tree in this way. Initially, T consists just of the source X, okay? And we have two possibilities for making the tree grow. You might have an F unsaturated arc from the set already settled S to its complement, and in that case, you add that arc coming from the tree to the complement, okay? You add that arc and the new vertex you have reached, okay? Other possibility, there exists an F positive arc going towards the vertices of one of the vertices of the tree, with which has F positive, so with a positive value of F, okay? In that case, you add that arc and the tail of that arc, and so your tree grows by one arc and one vertex. Okay. Now what happens if you, in this case, you always have unsaturated paths from X to every vertex you have already reached? What happens if you reach the Y by this procedure, then you have an F augmenting path from X to Y. Then what you do on this path? You pick up the minimum of the you pick up the minimum of the differences for the forward arcs and of the values of the reverse arcs, okay? And then along that path, you add that minimum, okay? And so now you have made your flow grow, greater, bigger than before, okay? And then you can start back and see whether you have the possibility of having another F augmenting flow, okay? For instance, let's see this initial flow, okay? You can start with zero flow, for instance, but here they have already an initial flow from X to Y, okay? And you see that it is actually a flow in the sense that the values of the flow are always less than or equal to the values of the capacity. Flow bold, capacity normal font, okay? And so now what do? We start from X, and we see that it's possible that this arc from X to V1 is an F unsaturated path. Why? Because this is a forward arc, and you have a gap between the flow and the capacity. Okay. All right. So we go up to here, and we can also label the vertex with this capacity if you want. Okay. Now again, you look for something either going from this vertex or X itself towards other vertices with a gap between flow and capacity, or arcs coming towards these vertices with positive flow. Here we have actually two, okay? This and this, no, sorry. Okay, on the right. The first we have this from V1 to V4, which is a forward arc, and you have a margin for making the flow grow, okay? So you accept it inside. And also here you have this one, which is a reverse arc with a positive value of the flow, okay? And now again, what do you look for? Now you look for something going from this, and this vertex towards other vertices with positive iota. For instance, this arc, okay? Flow equals 3 to 3, capacity equal to 5, so okay. Here it is. All right, and now what happens here? You have this reverse arc with positive flow. You take it in, okay? And now you have this going with the zero flow and capacity 4, and so you have it. And this is a breakthrough, as it is called in the theory, meaning that you have reached with your tree, you have reached Y. All right, so what can you do now? You can pick up, let's see here. Here we have 5, okay, as iota of this arc. Here we have 2. Here we have 1, okay. Difference between flow and capacity for forward arcs, and value for reverse arcs. So it's the single. What interests me is the single path from X to Y. So this is not of interest for us. So 5 here, 2 here, and 5 here, and 4 here. Okay. So 4 is the minimum along this path, okay? Again, 5, 2, 5, and 4. So now I can add 5, I can add 5 here, make this equal to, no, I had here 2. So 2 is our minimum, okay? Again, 5, 2, 5, 4. So 2 is our minimum. So I increase my flow by 2 along this path. So here we make it 3. Here we make it 0. Here we make it 3, and here also. Okay, so we have modified our flow along that path, and now we start again with the new values of the flow. All right. Okay. With the new values, and you look for, and you see, for instance, that you cannot find any breakthrough here. Let's see, 3 to 6. Okay, we have a gap of 3, but here we have 0. Here we have 2 and 3. We have a gap of 1. Here we don't have a gap. Here we don't have a gap between flow and capacity. So we can only make it grow with this one, okay? Here we are. Now what happens? Saturated, F0, saturated, okay? So our vertices now are X, V1, V4, and all arcs going out of these vertices are
at saturated, all arcs coming to these three vertices are at 0, okay? So our tree cannot grow anymore, all right? What does that mean? It means that you don't have any possibility of making the flow grow, so the last flow we have is actually the maximum possible flow that you have through the line. Okay? Break. 15 minutes.